So this section of the lecture is trying to further investigate about the operation of the motor. So last lecture, we have discussing about the basic connection concept and basic equation. So now then, let's see how we operate a motor and also how we control them. Can we make use of equation and control equation to look into the motors? So before we go further, then let's ask all of you about how are we going to drive a motor. Basically, we can use a DC voltage. You can control it, you can adjust the DC voltage. But more than that, how do we usually to operate a motor, a DC motor, control it? I think in the lab, you can also see that we adjusting the DC voltage using a DC power source. Then we can, what other way we can control the motor? Obviously, you know that for AC motor, we use an inverter to drive them. But of course, for DC motor, we're also using a controller, some controller. Later on, you can see the circuitry, how we use the controller to control the voltage, rather than use DC power source to adjust the voltage. That is impossible, right, in the real life. And another thing will be a DC motor can usually use for robot, or maybe for electric vehicle, or for many industrial drive. So we need to stop the motor somehow. When we stop them, we call it brake. How do we brake the motor? Would there be any better way we can control the motor to brake the motor? So that's something we like to see as well. And then for motor, apply the voltage, become a mechanical output. Then when we reverse them, then it can become a generator. So do you know all the motor, we can convert them into a generator? Or we can only, this motor must be motor, cannot be generated. What do you think? This gentleman, what do you think?
I think it can be a generator.
Because,
Because it convert electrical to mechanical and do it the same way mechanical to electrical.
That's true, exactly. So most of motor, 99% of the DC motor, you can reverse them straight away by controlling the mechanical, then locate the mechanical shaft, you can produce the DC voltage. So you can try the next time in the lab. When we have this kind of the motor operation, we drive them become rotation, reverse them become electrical. So they are almost 99% of the motor can do that naturally without too much complication. And then, however, you can see that when we operate the motor in such a way, we may need to consider winding. Before, in the last few lectures, we only consider motor as say the armature resistance RA, but now then we may need to think about the inductance. Because when we operate the motor in real operation, we are now controlling the motor probably by using an AC drive, DC drive to drive them. The voltage is not purely DC. Could be moving or fluctuating DC voltage. So in this case, the inductive device, inductive component for the motor no longer become fixed or unchanged. It may vary with the input voltage. The input voltage not pure DC. You see, when we apply pure DC voltage to an inductor, after you go to steady state, there won't be any effect. The inductor will just look like short circuit or pure resistance. But however, now you are applying a switching voltage, for instance, to a DC motor, the internal inductance may respond to your switching voltage. So that's a real case how we control the motor. So that's why we can look into that. The next point we like to look into will be about the motor torque. So we all know that motor torque are controlled by the armature current IA, right? Torque equal to K multiplied by IA. Then we can control the motor current. But now then, when we in the real application, how we control the current. So that's something we like to learn as well. And the next thing will be how is all that principle. Well, we learned last time, now we come into our operation, how we make use of the operation to control the DC motor. So that's all the area we might like to answer ourselves. Let's do that. So for the content for this talk, we're going to look into the operation mode and some basic method to control the voltage. Because DC motor mainly about voltage applied to the DC motor, then we see how we're going to control the voltage. Apply the voltage, we get the current. So probably the more basically, we can look into voltage control first. Of course, we do have current mode control, but basically we look into voltage. And then we look into dynamic operation for DC motor, what kind of dynamics operation, what kind of mode of operation a DC motor may have. So that's the order. That's the 4 items we're going to discuss. So firstly, we try to say will be a motor control is something we try to control the motor operation. So that would be like to look into the precise operation. If you just control the motor rotation, that's too straightforward. But what we like to do will be look into more precise mechanical operation. So that control can become from a controller, a microprocessor, maybe other control method. So that will be have certain high power demand for the mechanical work. So as you mentioned, for the point 3 will be, we can also control from electrical to mechanical, so the basic operation of motor. But reversely, we can also do the generation. So that means we can convert mechanical energy into electrical. So that could be done by normal power generation or from the braking or energy recovery. Because when a motor is going to stop, then you're not going to apply you don't need to apply any electrical power to them. Then the mechanical power can return to the electrical side naturally. So that's how operation like. So that means our motor control mainly is to how we control precisely the mechanical performance using electrical means, not just provide the rotational. In many cases, for example, like robotic control, we quite like to control exact rotation, angle rotation, or maybe exactly the linear motion, exact angle you're going to rotate, or exact position you want to control. So that's more look like why we need to learn motion control. So this motor in here is one of the best simple method we can control the motion control. So that means motion control is more fractional term. We're looking into the system. So besides motor control, we are now gradually move on to motion control. So that means we can precisely to look into what is the angle of movement, maybe also the linear motion. So that's also important how we control the motor. So that means in this case, we not just try to turn on and turn off the motor, so simple. We need to so-called the variable speed. So the control will be so-called, the speed will be controllable, so the speed will be variable. So that's why you may hear many jargon called variable speed control or variable speed joint VSD. So that's something you have been heard about in the past. So probably some jargon you may need to learn when you learn the motion control VSD. So that equivalent to variable speed joint. So that's a really important name jargon when you talk about any motor. So they will also mention about the VSD. So in this case, for functional control, you need to look in the forward motion and reversible motion too. And of course, the torque will need to be controlled. And in the future, or now we talk about AI control, intelligence will be important. We need to make sure the intelligence, just our precision is mainly about for precision, about the angle, and also positioning. That's called the precision, right? Of course, speed will be also precision control. And then when you talk about intelligence, you need to move all the robotic arm, about the position of robotic arm, robotic angle. So that's so-called more intelligent. We can go into the system. And then obviously the protection, the motion control, the motor drive is also not only provide you all the motion, but also make sure that the motor or electronic will be under protection. You're not going to apply with high voltage, high current to drive them, but you need to ensure that all this operation will be safe. And also protect from the power devices, the motor won't be over-driven, over-current, over-voltage. So that's something also need to protection. So that means a motion control, motor control, need to protect it from its operation, make sure you won't have any excess operation, like especially in the standstill to start the operation, usually the starting current will be huge. So we also need to protect from it. And also for braking, sometimes when you brake, huge current will be returned from the motor back into the electrical side. In this case, you may also need to make sure that there won't be too excessive current to damage your power source. So that means the key operation we're going to cover in this learning, including the speed control, how we're going to control the motor speed and control the motor direction, forward and backward, how to brake the motor properly, or we just turn off the motor drive, or there's another method to brake the motor, and also how to consider the motoring and also generating. Because as I mentioned, a motor can be either motoring or generation. More importantly will be the position control. That means the angle position and the linear position will be all these control method for the motor. And the position control also mainly depends on how good the motor is. Not all the motor could have very good angle and position control. Somehow we need to have a high performance motor in order to do that. For instance, a simple motor with only one pair of the magnet may not able to perform very good positioning. So we're going to discuss that. So, and for motor, if you look into the basic operation motor, the first one must be the motoring, how to control from electrical to control the motor to rotate, to move, right? So that means basically we convert the source, in here with the DC source, to convert into electrical energy to drive the load. So the load here can be electric vehicle, can be a gearbox, can be some mechanical system. So that's basic operation. Most basic operation is called the motoring. And the next thing will be regenerative braking. So now that when a motor running at a certain speed, now we want to reduce the speed because that's the so-called the speed control. Once we reduce the speed, then we need to so-called the regeneration will happen. So that means the mechanical power will return to the electrical side. So that's called the regeneration. During that case, not only return the mechanical energy back to the DC source, but we also have certain braking. Braking means the speed will reduce. So that's also, so the motor in this case, will also more look like a generator. So that means a DC motor, a DC generator are something similar to each other, actually the same kind of the machine. And next will be the dynamic braking. So somehow if you have a DC source there, you may not able to brake really well because you all rely on your motor to return energy to the DC source. Another way to brake the motor, we can disconnect it from the DC source. And then we can connect it with some other energy dumping. For instance, some resistor. We can dump all the power into another resistor. So that's another way we can able to return the mechanical power or try to reduce the mechanical power. For instance, if you're using electric vehicle, then your battery are fully charged. Then you can see that if a vehicle on the top of the hill, and then you want to go down the hill, of course, that will be power regeneration. You return all your mechanical power to your battery. So that's somehow we need to see that. But you can see that if you already fully charge your battery, then when you power regeneration, you return more energy to the battery. The battery will be overcharged, which we don't quite want because there's limitation for the top energy inside the battery. So in this case, you may not able to power regenerative braking. You may need to use dynamic braking. You need to dump the energy into somewhere, maybe a braking resistor. So that's so-called dynamic braking. We use other method rather than regeneration to brake it. So lastly, will be another braking as well called the plug-in mode. So somehow, if you want to further brake the vehicle rapidly, suddenly what one thing you can do will be you can drive the motor in the reverse manner. So here the motor is forward rotating, you drive the motor using another direction. So you force the motor to accelerate in opposite direction. So in this case, you can also brake the motor rapidly. So in here, you can see there's a 4 basic method you can operate the motor, but most common method will be motoring, the first one. Second one will be regenerative braking. So let's look at the circuitry for each one of them, right? So you can see in here, you've got a basic operation. So we look at DC source in here, apply the voltage to a motor. So that's how you operate. That's the most basic operation. Of course, in here, we're talking about separate excited, then you have few voltage, few control, you control the few current. So that's also really common. You don't need to really understand this part because they're talking about constant field of hybrid. So that is the most basic operation. So in this case, you can see that the armature current, the current for the motor, when you put the input voltage from the DC source, subtract from the back EMF EA, and then divided by the armature current. So that's the basic current. You can divide it from this operation. So obviously, when the motoring, then the input DC voltage must be higher than the back EMF, so that the current can be positive. So that means the motor is now consuming the energy from the DC source. So the torque, of course, will be positive. So in this case, we're able to have all the basic operation. So that's most basic fundamental operation for most case. Simple and straightforward. And the next thing will be called the power regenerative braking. So basically, you can see that if you want to brake the vehicle, reduce the speed for the vehicle, then that's the operation. Anybody can tell me how we can change the motor into such operation? I know when you motor it forward, and then now you want to reduce the speed, how you're going to become regenerative braking? If you are trying any situation driving the car, then when you release the gas, release the pedal, the vehicle starts to slow down. And that's called for regenerative braking. Everybody will tell you now we return the dynamic energy with electricity, which is this kind of thing. But what will say how we control the motor into this operation? What happens? What control you do in order to fulfill this regenerative braking?
Your time machine disconnected from your controller and then battery charging so you can there's no battery.
And
to
okay. So you see, if you want to mold at a certain speed, then you have a certain depth in that fixed voltage. We have constant speed. So usually this voltage, just before you brake the vehicle, this source voltage will be slightly higher than this voltage. Now then, if you want to brake the vehicle, what you can do will be, if you reduce this voltage slightly, for this voltage 100 volt, this will be 90 volt, right? And that's normal operation. The current higher will be forward, torque will be forward. So remember, it's 90 volt. Now my controller will reduce this voltage with just less than 90, maybe 55 volt, maybe 80 volt. Then this voltage will be higher than this voltage. Then the current will be reversed, taken out from the motor. Then will be the so-called the regenerative braking. The motor itself, the back EMF, now look like a generator to generate voltage back to the power source. So what you need to do is just to reduce the source voltage slightly less than this motor voltage. Because this voltage controller, you have controller for control voltage, not a power supply, but you have power controller to regulate the input voltage. Or even though you have power source, you can reduce the voltage. You can see how you regenerate the power. That is the power source. That is how you operate. Of course, all that things will be done by some control electronic engineer. So the more you reduce this voltage, the more you can brake the vehicle. How we generate. That's how the internal structure looks like. But of course, all this will be done by control electronics. You get that? Do you get my point? Yeah. So the concept will be simple. Just reduce the power source. Yes.
I have a question. So the end is the voltage from the controller, it's not from the battery itself.
Yeah, that EA, right, is governed by the equation. You see, the barrier equation equal K multiplied by speed of motor. So that means for certain speed, when you control motor up to certain speed, say 3,000 RPM, that will fix motor. So with 3,000 RPM, you get certain EA voltage that will fix them. So now then you want to reduce the 3,000 RPM, what you should do, just reduce this one less than EA. Then the energy to go back to the power source, the voltage 3,000 RPM need to be reduced so that these two voltage will match up. So for instance, this 90 volt, this 100, 90 volt running at 3,000 RPM. Now you reduce this voltage to 80 volt. Eventually, this voltage need to catch up with this voltage. So to reduce from 90 to 80, then the speed must be reduced. Get my point, right? Never you get it?
Yeah.
Okay? No? Again.
So for instance, during that time, at any instant, that's an 80 volt. And we have, say, 1,000 RPM. So now then, so for instance, 90 volt. When at 90 volt, our voltage here will be 100 volt. Yeah. So that's normal motoring operation. Now I want to reduce the 1,000 RPM. What we need to do will be, instead of 100, I reduce to 80 volt. So you can see that we have 90 volt, this higher voltage. So the current will therefore go back to the source. Eventually, when the energy return to the power source, this EA voltage gradually reduce to 80 volt. Then of course, 90 volt, 1,000 RPM. Now if we move on to 80 volt, then this voltage will be therefore reduced because EA equal to K phi omega m, right? So that is, this will be fixed, then the speed need to reduce in order to match up with the back EMF. Eventually, when you connect two voltage together,
This is not 80 volt, originally 90 volt, so this will be reduced energy to match up the power source. So that will eventually reduce to 80 volt. If you reduce to 80 volt, then the speed need to be reduced. You get it? So basically we say this is energy source with some vocational energy. Motor will take the constant, but some energy and the energy will be saved 90 volt to certain 1,000 RPM energy. So now then I'm going to take this energy out by putting the 80 volt to X energy. So how we do that? When the current comes out into here, is energy reduced. How energy reduced? Because the K omega will be reduced from the omega equal to 1,000 RPM down to low voltage. So you can consider it as an energy source in here. Gradually being taken out. How we take out the energy? By the left-hand side, we are using a lower energy potential to extract this energy out. That's basically how it operates. So you can see that if the input voltage V in have higher voltage, you force the energy to the motor. If a low voltage, then the motor, you extract the energy from the motor. That's how it operates. So motoring means this voltage higher than this one. Regenerative braking means this voltage higher than this one. All right. So that's how we can see two energy sources here. Which one higher than which one to control how the current moves. Any other question? Do you have that concept? It seems a little bit, and not quite sure. Maybe that's the first time you learn the motor drive, right? I guess. So, and also motoring is quite simple. Let's try again.
So first one is the motoring. Motoring, that means, for instance, you have 100 volt here. And then you power up the motor. And the motor will eventually reach certain speed. And then now the back EF equal to 90 volt here. And this will have a 1000 RPM, for instance. Of course, the voltage drop here will be 10 volt. So that's normal operation. You apply 100 volt to the motor from the power source, from the DC source, then you measure the back EMF, come up to be 90 volt. And we know that the back EMF here, EA, is equal to K5 omega M. So that's how we get that. If you want to increase the motor speed, you apply high voltage, then probably you will have high voltage here, you got high voltage here. Low voltage, you got low voltage here. That's how we control the motor speed. So that's normal motoring. And then you can see that the input voltage must be higher than the motor voltage back EMF. Then this current will be positive forward to the motor. And the energy, you see, what's the power for VE? VE multiplied by the 5A will be the input power. So that's why for motoring, the power input will equal to V in times IA, right? So that will equal to positive. So that means we deliver the power to the motor. Okay. Then the input power higher than the motor. So that's normal operation for motoring. So, but now then, we are converting. We want to reduce the speed of the motor. So like that. So now then, you can see that in here. Be clear. So if that is 90 volt here, then if this voltage is greater than V in, so what you need to do is you can 90 volt here. If we reduce the input voltage to 80 volt, V in is a controller. It's our input control. I can control any voltage. So now then, instead of 100 volt, I reduce to 90. So that is to say the motor voltage will be less than input voltage. So the current will moving in this way. The current is going this way. Then you can see the power of the motor will equal to EA multiplied by IA, right? You can see that the current is moving outside to the left-hand side. So that means power coming out from the DC motor. So that means this motor is now called generating energy. Because the energy, the current come out from the motor.
Is negative that equation, and you know it's a general, right?
Then you see the current. You see that's a voltage source. The current moving in this direction. So when the current coming out from a voltage source, it must be generating power. So that means it's called regenerative braking or regeneration. So energy come out from motor. And then you can see that for DC source here, we now current go inside the battery. Look like charging the battery, right? So we now generating from the motor to the input DC source of the battery. So that's how we make it. So one thing you can see that will be you can check the current direction. The current direction here will be the current moving in this way. Why moving this way? Because this voltage EA higher than V in. So that's why current moving in such a way. And then that's why the current, you can just calculate the current by this formulation. The key thing you can see in here will be which voltage higher than which voltage to determine the current direction. To determine which one is the generating the energy, which one will be receiving the energy. Any question in this point? You need to understand the generation concept, the voltage generation concept. Yes?
Will I see that the polarity is defined on the circuit. Will that always be true? Or when you, if you give us a question, will the polarity be defined? On the diagram.
You see in here, both of the polarity hasn't been taken. They both are positive in here. The key point you need to find out in this will be this is still positive here. This is still positive. But the amplitude of this positive will be different in both in either case. So
We haven't changed any voltage level. We haven't changed the voltage polarity yet. So in this case,
you can see that in here, that is also positive voltage. This is also positive voltage. But in here in motoring, we having higher voltage applied to the motor. And then this motor must be higher than the back EMF PA. This back EMF PA is the internal voltage from the motor. We call it back EMF due to the rotation of the motor. So all the mechanical energy are actually derived from this PA, which we see that from last lecture angle. So that means for normal motoring operation, so the input voltage Vin is to any kind of motor, so Vin voltage must be higher than the EA voltage, so that the current IA can be forward to the motor. Okay. And then of course we can put it, flip it vertically. Now then, for power regeneration, this compared to this one need to be changed.
so that will be the next slide. In here, right?
So now then, if you want to the motor become regenerated, so then the EA voltage should be higher than the input voltage. How we do that? We just reduce the input. Usually we cannot reduce it because it is supplied by a battery or supplied by other control, but we can actually using control system to reduce the input voltage. So our controllers for the input voltage, we try to have a higher voltage for motor, and then we do the DC voltage or regenerated for that half operating. So the key point for this two page will be mainly to tell you the difference between these two, EA and VE voltage. How we adjust the input voltage as relay and the EA to control the current be forward or backward. That's the one is just better. So better. Is better. And one thing which we yes. So could say again? That will be experience line. The experience line will be, we're going to talk about the tracking mode. That will be experience line. We'll talk about the position, the polarity for the motor. It's really important on two sides. Yes. So now then, firstly, you understand the mode of operations, motoring, and also the regenerative braking. So that's two important operation mode for the motor. Maybe this gentleman will tell me what's the difference between motoring and regenerative braking.
Motoring, we want to have the voltage input, the voltage of the higher motor so that we could, like, we want to go forward there. But for braking, we want VN to be smaller so that the energy from the motor feed back into the controller, back into, is it back into the battery?
Yes, yes, I often. So once they do that, you can therefore using this relative voltage to control the motor down, motor current direction. So if you forward motoring, the current direction will be from the battery. If for the regenerative, the current will be from the motor back to the battery. That's what we make. Okay. How about you? It's very simple concept. I won't ask you in the exam because there's no equation here. So only one simple equation. Like you do need to understand the concept. But after you've done the motor drive for some time, you should be able to get it. The concept will be same in the same. I think electric vehicle for the same. So when we drive the motor, drive the vehicle to forward, then of course we have high voltage to the motor. The motor of course will pay forward. But now then, if you want to brake the vehicle, brake the EV, So we try to reduce the supply voltage to the motor lower than what it should be. Then we can see that the motor energy will return to the battery. So that's it. Yeah. So under that case, you can see the current will be forward or backward. Yes.
Can you take the and then turn it like negative, like invert the voltage on it?
Yes. That would be the 2.4. We're going to talk about it.
Oh,
So the first two mode will be most important. 2.1 and 2.2 most basic operation for this motor or for all the motor. So 2.1 is motor, really conventional operation. 2.2 when we reduce the battery energy by so-called the regeneration. So that's the most common mode of operation for all the DC motor.
So next, 2.3 dynamic braking. Also, you can see the diagram also quite straightforward.
Instead of using a battery here, okay, when I say battery, that may not be a battery, can be a DC source, can be a controller to produce some voltage. But a simple there, I'm using a battery, easier for us to imagine what it is. So now then, instead of using a battery here to power up the motor, we remove the battery, connect with a resistor. Of course, in this case, we can also dump the energy into the resistor instead of return to the battery. So that's so-called the dynamic braking. So obviously you can see that we can also right now the equation will be the EMF divided by the summation of the two resistors.
Very simple, straightforward. Of course, you can see that the current now is now going in this way. Because we are dumping the energy to the resistor. So why we need to do that? How we can able to do that? Two ways we can reduce the motor speed. One way will be using 2.2 regenerative braking, like what we mentioned before, reduce the battery voltage. Another way will be just putting a resistor. Also be okay. So in many times when we want to brake the vehicle, electronically we can use a resistor. One of the key features will be, then you may ask you, why don't I use the battery to do that? You can use either way to do that. Using battery is good. It can return energy to the battery. But this way will be, somehow we have difficulty to brake using low voltage. For instance, like vehicle we fully charge up to 100%. We can't reduce the voltage further. We can't charge the battery further. The easy thing to do would be using braking resistors. So that means for all the vehicle designs, the users tend to use the regenerative braking 2.2. That's the most common way we reduce the speed of brake the vehicle. But you can see some case when we fully charge the vehicle, we cannot further charge the battery by using braking. We cannot further pump the energy to the battery. And what we need to do is putting on resistor for last minute of the to brake the vehicle. Because fully charge could further charge up the battery, will damage the battery. Can be dangerous, but putting resistor that can be done. So that's in all the vehicles they do have that function to brake it. Or maybe for some very simple motor driver, they don't have any good capability to use power regenerative braking. They just put in a resistor to short the terminal. Then you can also control the motor speed. You can therefore regulate this resistance. You can control amount of current. So if this is regulable, so the current can be controllable, then we can also control the motor speed. So this is also quite simple and straightforward. You can use it to regulate you can also use this method to regulate the motor speed. This page will be simple, right? Straightforward. So that means if you have when motor running at certain speed, one thing you can do will be remove the power source quickly to connect our resistor to dump the energy to resistor. So you can, once you can see the current are moving in this direction, so then the energy are coming out from the motor. Of course, the speed can be reduced because the energy is holding by the motor relates to rotation to the speed.
remove the energy, reduce the speed. So the basic equation will be just like the EA divided by the summation of the total resistance. All right, any question? This will be straightforward, right? Yes?
You can explain why big difference on it compared to the other three.
So just now I mentioned about we try to use as much as we generally break it. We get the best way because we don't pump the energy to the system. We store the energy in the battery. That's the best way to do. So 2.2 is the best way to do. But in some instance, when we're going to have alternative way to break the vehicle, like very simple control, we don't have complicated controller to allow the energy return to the battery, or we fully charge the battery 100%. We cannot further charge the battery because then we damage the battery. Then we dump the energy to the RV system. Yes?
Is this just a simple like switch where,
It was okay. All the vehicle would be like, even though in the future when you design your EV, you will never know you first day operate the EV, fully charge the EV, right? But now the suddenly if you are in the top of the mountain, you're going down the hill, then you further charge your battery, that will be disaster. So you have to look into something is RV, just for insurance. You will never know. Or sometimes you get braking for long time before you charge the battery, then you have to dump the energy.
So that's in many cases you may need to use that. So that's also called dynamic braking, or in many simple motor drive system, they don't have any good circuitry for power regeneration. And then you can imagine the most simple way would be remove the battery, connect with the system. That's also good. But bear in mind that with energy, power, thermal issue for that is R, I squared R. So that means you need to have cooling phase to flow into the system to dump the energy. So that's something we also need to be considered too. So that is straightforward. Next one called the parking mode. So that's many one would like to discuss. So one thing would be, why don't we reverse the polarity for the driving motion? Then you force the motor to rotate in opposite direction. You can also reduce the motor speed. That's straightforward, right? So this mode called the parking, like what you just now asked us. So then you can see that there's a three way you can reduce the speed. One way would be regenerate the braking, reduce the motor, reduce the applied voltage. Next will be using resistance. Third will be reverse the polarity. So we're using opposite direction to drive the motor, force the motor to rotate in opposite direction. Of course, we can reduce the motor speed. So this mode we call the parking mode. Also very popular operation. But here you can, the concept will be quite simple and straightforward. You are able to rapidly, really quickly to reduce the motor speed. Because regenerative braking is also quite slowly. But if you want to reduce the motor speed suddenly, rapidly, within fraction of a second, then you can use the parking mode because you force the motor to rotate in opposite direction. But of course, we don't like that. We don't like this mode of operation. Why is that? Huh? Sorry?
Of course, I so here, right? Don't look at this. Don't look at my thing here. Why the motor get very hot?
Because the numerator being plus EA is very large. Many times ours.
For example, yeah. When we read the polarity for which can be here, this will some act together with a high voltage applied to the motor. So here RA is not external resistance, it's the internal resistance of the winding. So you are now applying so that but on the voltage to the motor winding. The motor gets really, really hot. So then you don't try to do that unless in the last moment you cannot break the vehicle, you have to just parking mode to instantly sudden braking to the vehicle or the motion. So we don't use that not until the last millisecond. So the current is built.
So that's, you can see we now discuss to you 4 common mode of operation. The first one is the normal operation, motoring. The other 3 will be for braking, reducing the speed. The last one, 2.4, plugging, is the most rapid way to reduce the speed. On the equation, you see that that is something we don't quite like, but it's the really powerful braking. Don't do that often, when you burn the most likely. But all the motor drive have that capability. Any question? Yes.
Do you know any existing applications of loading like that?
All the motor drive that you have at this kind of operation, they all need to be that. So normally when you break the vehicle, when you try to drive the EV, you try to get EV from your friends to drive and or this semester, you can join my course on EV, electric vehicle design. Very welcome you to join my course, electric vehicle design. It's best course in the whole United States. You see, not that many professors focus on electric vehicle. I'm the one who worked on EV for more than 30 years. So you join my course, you learn something. But anyway, so when you try on electric vehicle, when you press the pedal, then of course the vehicle will speed up. So when you release it, the vehicle will quickly to go to power generators, which will be move on to. So the vehicle will quickly go to power generation. But when you release the pedals, the system will be the input from the motor drive circuit. Then that is break the vehicle. And then you find that the vehicle go to near to the traffic light, you need to stop or has some pedestrian there, then still not able to brake it, you need to press the brake. So the brake has 2 functions. One will be the mechanical brake, another one will be go to the braking mode. Yeah. Which reverse the voltage so that you can reverse the operation with the vehicle. So there's a manual operation in EV depending on how we design it. So check already says the EV operated. Of course, that's not favorable. So that means usually when you operate on EV, then you are just using the gas, the accelerator that good enough for overall operation. Accelerating and the brake also can be done. We call it the single pedal control for all the vehicles. 80% of EV are using this method. So now then we have 4 basic operations. So now then let's see, there's a concept, how we control the voltage from the motor input. How actually look like. So now then I show you the circuitry, how the circuits look like, right? So here will be the motor equivalent circuit. And that's a driving circuit. Before we use a battery to show you the DC voltage, but never become a single battery. You need to change the voltage for the battery. For instance, your battery source here, you pass through some control system, control the electronic. I will show you what that circuit is like. Then that will control this voltage to a variable voltage to try and motor. You need to use variable voltage to try and motor. You're not using a resistor to change. You're not using and not to control the voltage, but we use power electronic to control that. So we go to implement some control the electronic power control system to vary the voltage apply to the motor. And then for the fuel circuit as well, you can usually we don't use DM to expensive, and then you can use a field controller to control the field to the motor. So the field control circuitry also something for DC saw, we control variable voltage with the field. So that's basically how the representative circuitry look like for the DC motor. So the power driver actually is some control system, control electronic. Next page, I will show you how they look like. So first of all, before we go further, we will see how we control the voltage. I think that's understandable. So instead of a DC voltage, you see this waveform. We have the waveform, we call it this square wave. Then in this voltage, we turn a high voltage for this amount of time, and turn off, and turn on, turn off. So the work rate we apply to a DC motor is not DC. We are not moving the DC motor up and downward. We are using a square wave like this to apply to the motor. So that means if you can see that square wave applied to it, then you can tell you about the some parameter here, the duty ratio. The duty ratio for this waveform is the turn on time divided by the period of the duty ratio B. So that's a common name we use for the switching electronics. Then you can see the average voltage applied to them will be the turn on voltage. So like this actually is called V on multiplied by the duty ratio. It will provide us the average voltage. So this is the average voltage we apply to the motor or apply to another system. So that's simple and straightforward. So this waveform, because we moderate the pulse width for the waveform, then that means we call it PWM pulse width modulation. Okay, so remember this waveform is really, really simple, but however, you do represent simple operation of the system. And then the equation we call the average voltage will equal to D multiplied by V1. So bear in mind that you can actually adjust the duty ratio from 0 to 1. So the ratio for D is called from ratio 0 to 1. So in theory, you can adjust the V1 voltage from 0 to 100%. So that's a really powerful method. So all these things are done by how we trying to control the input sign for the DC motor. So that's the basic concept. Very simple, just show you we are always using this method to do the job. All right. So the waveform can be anything. Just like I showed you the waveform more look like 60% of duty ratio. But the waveform can be any duty ratio. Like here, you can use a really small pulse to control voltage. If you want the low voltage, maybe you want to break the motor, you can use really low voltage like this. Even tiny duty ratio also be okay. So let's look at this waveform. It's very straightforward. I still need to show you about how we calculate the duty ratio, right? So a waveform of the VB, the amplitude equal to 10 volt, you control it by the switching driver system, and T1 is 0.2, T2 is 0.8 milliseconds. So calculate the duty ratio B and the period frequency and the average voltage of the PWM waveform. Very straightforward to make a simple ratio, right? But I just show the concept because although really simple, I still like you to understand how we use the PWM operation for motor. So that means duty ratio, of course, the ratio for the pulse here divided by total length of treatment. Here T2 becomes 0.2. So that's the ratio, 30% or 0.2. So that's the ratio for the waveform. And then the period will be T1 plus T2. Obviously, will be 1 millisecond. We also like to mention about the switching frequency. The switching frequency is a really common terminology we use for the motor drive system. And of course, the equation will be this, right? For over. But okay, first. You see for motor drive, anybody can tell you what's the most common frequency we drive a motor. So what do you think? What's the most common frequency we drive a motor? What you always on? No, the frequency of operation. No, the frequency. Here I give some tips already. The frequency we drive a motor, the waveform not DC. But usually we switch waveform like this one, say 1 kilohertz, one of the common frequency we drive motor. So any example here will be highly related with the technical example of the number. But 1 kilohertz is only one example, and then the common frequency we drive can be from 1 kilohertz up to 100 kilohertz. Can be quite a wide range. Yes.
Is there some functional requirement on like the resolution of the motor that governs like the common operating frequencies?
You don't. The frequency operation will be just, you can see that's the waveform, common waveform will apply to the motor. Like in here, we apply this waveform to the motor. So this waveform will be going to appear along here. So this waveform, the square wave, we apply to the motor. So that's basic waveform apply to the motor. Let me finish that first. This waveform, and the waveform is usually what I mentioned is square wave, and then you call it PWM pulse width modulation. So the pulse width modulation ratio, we call it duty ratio, can be like this. This more look like 60% duty ratio. This more look like say 0.2, 20% duty ratio. So duty ratio can also be varied from in theory from 0% up to 100% anyway. The frequency operation, as I mentioned before, can be from 1 kHz up to 100 kHz will be common. So the common frequency can be from 1 kHz up to 100 kHz. Of course, there's no fixed definition, can be anything. So John, what did you ask?
I was gonna ask if the frequency would depend on the motors, it would just depend on the variable speed drive, right?
That's true. So the frequency applied to the motor depends on few items. First, depends on mode. You see the motor able to respond to that frequency. If the motor is too large, it just don't do 100 kHz. Say, for example, that motor for train application, large vehicle, then we can probably 1 kHz, a few kHz. But for some high-speed motor, for example, like for some industrial drive robot, we need to use high frequency, maybe 50 kHz will be quite common. And as I mentioned before, usually most of the motor operations will be 100,000 RPM. But nowadays, we gradually move on to a high-speed motor, maybe 30,000 RPM. Then the frequency applied to the motor will be need to be even higher frequency so that they can be compatible. So that's normal operation for the motor. So then frequency 1 kHz, that's how we measure about that. So more importantly, will be average voltage. What's the voltage actually applied to the motor? Then you can see that here we use 10 multiplied by 0.22 volt. So that's to say we are using this so-called PWM to adjust the average voltage to the motor 0. That will become 2 volt. Right? So you can see that if the duty ratio, the D, is now 0.2, we can use from 0.1, 0.2, whatever, from 0 to 100%, we can adjust the voltage. So the VB voltage is 10 volt, but can be, after we use duty ratio control, can be from 0 volt to 10 volt. So that's the way we adjust the voltage in large range for the motor control, for motoring, regen, maybe for other voltage. Yes?
Is there functionally a difference between PWM and an analog voltage input?
We don't use analog. Why is that? Because you can see, later on, you can see the circuitry. We all use PWM because we are using switching electronic. So this technology we call power electronic. So this field of study called power electronic. So that is to say, we are now trying to control the voltage, switching the electronic, so that we either have the full voltage, say in here will be 10 volt or 0 volt. We don't give you any linear or analog voltage to both sides. We don't do that because it's difficult to generate this voltage and a lot of power losses. So all the power electronic, all the motor drive system are using this so-called switching electronic or power electronics. Yes.
So it's because of simplicity for the making of the drive or the driver.
That's a really good question. Why we want to do that? Because mainly the efficiency. For switching electronic, power electronic, we're able to produce converter 99% efficiency. But however, if you look into analog electronic, then you can see what's the analog electronic? For instance, in here, we got 10 volt. Analog electronic will be, I want to reduce this voltage to 2 volt. What we can need to do will be putting a resistor here to dump the energy of 8 volt into here. So that means this is the losses. So analog electronic will be, you're putting a variable resistor or maybe some variable resistor, whatever. You try to, as a potential divider, to reduce the voltage. So although output is full volt, but the rest of the voltage will appear in this receiver 8 volt. That means you're wasting the energy. So analog electronic will reduce the voltage. Not useful because you waste the energy. But using power electronic, later on I'll show you, they will, in theory, they got 99.99, 100% efficiency. They don't waste any energy. So that's why all the motor joint we are using this kind of power electronic technology. So we don't teach power electronics at the moment, but this first line will give you some very basic introduction to power electronic, how we control the motor. I think for next semester, not next semester, I think the next power electronic course will be in 42026. 2000, yeah, I think that's also a mandatory course. So do come to my course, then you know what it is. So anyway, so we are using switching electronic or power electronic to control the voltage in perfect manner without any power losses. So that is the technology. We don't use analog electronics. So next, we can see that. So now then, the typical circuitry to connect the motor will be like that. That is really simplified circuitry to show you how we're able to produce the switching electronic. So the left-hand side, we see that we're only using a switch S and also a diode. We are able to produce the switching output instead of a pure VDC voltage. So here will be VDC voltage. But now then we're using this and that. The voltage Vm for the motor will therefore become this voltage. We're going to see this voltage in here by using turn on and turn off the transistor. So basic operation will be really simple for that. So you can see that if this is turn on, if this is on, if the switch is on, then you can see that this voltage must be equal to this voltage. They look like short circuit. Okay, when this on, so that means therefore the motor voltage equal to VDC voltage. Simple enough, right? And the next thing to do will be if you turn off this, if now become off, then why the motor voltage becomes 0? To the diode. Key thing is you see a diode here. One thing we can notice that will be IA current is the motor current. Inside the motor, there's an inductor. So the current inside the motor cannot stop instantly because the inductive current need to continue to flow because it has its own inertia. So this current, when the S is turned off and move on to here, then this I current need to continue to looping in here, continue to flow. So this current will therefore flow to the pass through the diode D. So the voltage drop on the diode will be really small, more look like 0 voltage. Maybe 1 volt, 2 volt, we don't care. So that means Vm will therefore become 0 volt. So that to say the voltage appear in here, the peak voltage equal to VDC, and this voltage equal to 0. So that's how the motor voltage will look like when we're using this simple switching circuitry. So we call switching electronic or power electronic. That gives you a very basic concept how we control the motor voltage. Do you get that? Okay. So do you understand this full logic? How we can get the voltage across the motor Vm become either full voltage or 0 voltage. You get it? Not too much time. We can repeat next time, make sure, but the logic will be straightforward. When we so case A, case 1, so we could this connected. Case 1. Case 2, then we are looping in here, case 2. Looping here, because diode was shorting the circuit. Diode conducting means 0 volt on the motor. 0. So that means the motor can either equal to VDC or 0. That's all, right? So we go back to think about that and ask you again, and explain to you again on Wednesday. Okay. See you then. Bye for now.